All right, welcome back. This is a short lecture on the very basics of chemistry and sort of what you should expect from this class in chemistry. One thing I will tell you about this class is that AP Biology is kind of the combination of what you learn in Biology 1, what you learn in chemistry, and we're going to kind of smush all those things together so we can go way deeper than you ever went in Bio 1 to try to explain how those processes actually work. Now, what you're looking at here is a periodic table, and I really hope that this looks pretty familiar to you. On this right side, we have our nonmetals. On the left side, up till we get to this black zigzag line, is where we'd have our metals. Don't worry about any of these things down here. We will never be talking about those in this class. Right along the black staircase line is our metalloids. We don't really go into those. What we focus on mainly is right about here and a few of these guys over here. Now, one thing you should know, hydrogen, while it is on the left side of the table, is what we call a nonmetal, so that one doesn't really follow that pattern, but everything else pretty much follows that pattern of metal on the left, nonmetal on the right. This is one of the boxes that we see a little more up close. This is fluorine. Fluorine, up here we have the atomic number, which is 9. This is the atomic mass, which is 18.988. And for the purposes of our class, we just round something like this up to 19 just to make it a little bit easier. And these two numbers give us a little bit of information. This is the chemical symbol. Fluorine is just F. Most chemical symbols are 2 letters. Some of them are 1 letter. A lot of the ones we deal with in this class are just 1. Um, when I'm asking you what's in the nucleus, hopefully you should be able to tell me, yeah, you better find your protons and your neutrons in the nucleus. Outside the nucleus, that's where you better find your electrons, and shells, we'll talk about those in one second. This is a very rudimentary model of what an atom looks like. I will be the first one to tell you that we're not really telling you the whole truth on what an atom looks like when we look at this. There's things called p orbitals, s orbitals, d orbitals, all of that stuff. That's higher level chemistry than we're ever going to go into. If you can understand how this model works, that's kind of the basis of what we need for AP Bio. Again, protons and neutrons in the nucleus, electrons floating around the outside of the nucleus. That's the basis of what's going on. Protons tend to carry a positive charge, electrons carry a negative charge. Neutrons, you'll notice, nothing inside of here, so the neutron has no charge or it is neutral. When we are talking about the different shells or different levels or clouds, however you want to say it, when we're talking about electrons, in that first level, you can only hold up to 2 electrons. In the second level, you can hold up to 8 electrons. In the third level, for the purposes of this class, we'll say 8 as well, but we'll never even get that high in this class. We typically stay in the first and second level. When we say they can hold 2 or 8 electrons, that has to mean that refers to that atom being stable. Atoms are most stable when their electron shells are full. So if I have an atom that only has 2 electrons and they would only fill up that first shell, that atom is pretty stable, and that atom with 2 electrons is what we call helium. Hydrogen, on the other hand, only has 1 electron, and it's not that it's an unstable atom, but what it does is it's really willing to give up that electron to make something else stable and make itself sort of happy. Elements with 8 electrons in that second shell are really happy. If it's got 7, it's going to want to take an electron from something else. If there's 9 electrons total, where you have, 11 electrons total, where you'd have 2 in the first shell, 8 in the second shell, and 1 in the third shell, well, it would be really willing to give up that 1 electron. And that's sort of where this interaction of different atoms happens, and that's sort of the basis of this class. So we're going to talk a little bit about how that stuff all goes on. Now, when we talk about living things, most of biomass, or bio means living, mass is material, living material is made up of these elements. Hopefully you know C is carbon, O is oxygen, H is hydrogen, N is nitrogen, P is phosphorus, S is sulfur. There are a lot of other elements involved inside of each and every one of you, but these ones are the big ones. And these ones make up a lot of those molecules that keep you running and keep you going. When we put atoms and atoms together, they make compounds or molecules. It's a molecule when it's two nonmetals combining. It's a compound when it's a metal and a nonmetal combining. So if you talk about that left and right side of the periodic table, you should be able to tell me if it's a compound or a molecule. Hopefully you'll remember this from chemistry. What's it called when electrons are shared? Well, we call that covalent bonding. Covalent bonding means the electrons get shared, and realistically, most bonding is a form of a covalent bond. Even though we say ionic bonds, electrons are given or taken, it's really more of a covalent thing. We'll get to that another day. But covalent bonds happen between two or more nonmetals, and there can absolutely be more than two things that are covalently bonded together. And we'll get into some very large molecules very soon when we start talking about our macromolecules. Bonds are three-dimensional, which means that they're not in a flat plane. That's one problem with looking at molecules on a flat board or on a flat piece of paper, is that you don't really get the respect for how the angles and everything is sort of holding everything together. When we talk about covalent bonds, they are very stable because the electrons are being shared sort of equally, but sort of not equally, and we'll talk about that in 1 second. And you can either make single, double, or triple bonds. Carbon is a great example of an element that bonds a lot of different ways where you can make those single, double, and triple bonds, and we'll look at some of those in class in the next day or two. When oxygen bonds with itself, or a molecule like oxygen, meaning the same element is bonding with itself, those electrons are shared equally between the two atoms. When we have different ones going on, they're not shared equally because of something called electronegativity. Now, when you look at the periodic table, electronegativity increases as you move to the right of the periodic table and up higher on the periodic table. And we don't look at that last column. Those ones are the noble gases, the ones underneath helium. So if we're talking about the most electronegative atom on the periodic table, that's going to be fluorine, sitting up there at number 9 at the very top right of all of those things. The ones that are more electronegative, it's kind of like being cool. The electrons want to hang out with them. So more electronegative you are, that means more electrons are going to be in your area of the compound or the molecule. If more electrons are on your end, that can create a kind of polarity where you have more negative charge on one side of that molecule than the other side at any given time, giving it kind of a charge and create some kind of polar stuff. And we'll talk about that more when we get into water. There are other bonding styles. Ionic bonds, we say electrons are given or taken away between two different atoms. That happens between a metal and a nonmetal. And there's also something called a hydrogen bond, which isn't really a true bond. A hydrogen bond is an attraction between polar molecules. When we talk about water, we're going to go much more into that because hydrogen bonds are extremely important for what we're going to be talking about in this class. But again, hydrogen bonds are an attraction. They're not a true bond, but they form a lot of things in nature and in the way that our body works. So it's a very important thing that we look into as we get started in this school year.